In this video, we'll be taking a little bit of time to talk about how to build a slope field from scratch. In the prior video, we introduced the slope field, talked about the relationship between the differential equation, the solution to it, and the slope field. But in this video, we'll talk about building one of these from scratch. Now, if you're taking Calc 1, if you've taken AP Calculus, you may be asked to build some of these by hand on an exam. AP exam has definitely done that in the past. If you're in a differential equations course, if you're doing this for an engineering problem, you're going to be using software more likely than not that is capable of building these. The Desmos website is able to build these. But if you're going to be building them by hand, here's how you go about the process. So like we said in that video that I just referenced, the slopes that you see for these little line segments that form the slope field are determined by the value of the derivative. The solution that fits into a slope field has to have the slope indicated by the segment that sits nearest to the point that it's passing through. So the way that you build one of these from scratch is you're going to have a section of the coordinate plane that you're asked to deal with. So in this case, we're going by 1 unit each for each of the tick marks that you see here. So I'm going from the y-axis over 1, 2, 3 units, and then to the left 1, 2, 3 units. And then from the x-axis, I guess, down 2 and up 2. So I'm going to have a bunch of segments that I'm going to have to consider. The good news is that with a lot of differential equations, when you're building a slope field this way, there's going to be some patterns that you can exploit, and we'll go ahead and we'll talk about those here. So when you first start building these, it might not be a bad idea to think about it in table form. So I picked this corner here to begin with. So at the ordered pair 3, 2, what is the slope of my tangent line for the curve that has to have this derivative? So all I did is I plugged 3 in for the x. There was no y to put 2 in place of, so I didn't really have to do anything with this. And then I got 3 plus 1, I got a slope of 4. So I did my best with this blue line segment that you see right here. I was doing my best to try to show a slope of positive 4. I have to decide where I want to go next. I'm eventually going to need to have all of these slopes indicated as you see in the completed slope field. What I chose to do is I chose to go to the left. I could have gone down. If I go to the left, what ends up happening? Well, when I go to the left, my y value stays 2. My x value has decreased to 2. So what's the value of my derivative? What's the slope of my tangent line to something that has this derivative at this point? Well, I put 2 in for the x. There's no y to replace with 2. So 2 plus 1 gives me a slope of 3. So I was doing my best here to try to show a slope of positive 3. And you can see if you compare the slope at this spot to the slope that we were discussing a few seconds ago, it definitely looks like it's decreased a little bit. It's kind of clunky to do this by hand, and that's why when you get the really advanced ones, you're going to be using computer software to build them. But I have a slope of 3 here. That was a pattern that I think I latched onto right away, because if I move to the left, x is decreasing by 1 unit, y is staying the same, but this differential equation doesn't even depend on y at all. So if I move to the left again, this slope is going to have to go down by 1 more unit because x has gone down by 1 more unit. Right? So if I had this written in at the ordered pair 1, 2, what I would end up with is I would end up with a slope of positive 2. So as I move to the left 1 unit across any of these horizontal lines, what has to happen is my slope has to go down by 1 unit. So I have a slope of 4, slope of 3, slope of 2, slope of 1, slope of 0, slope of -1, slope of -2. I then move down to my next row. Now here's where it gets really easy, because for this particular slope field that we're building, the derivative only depends on x. So if I go down to this point where my y value is now 1, but my x value is still 3, I'm still going to get a slope of 4, right? If I put 3, 1 into this derivative, the only calculation that has to happen is still 3 plus 1. So 3 plus 1 gives me 4. The slope here has to be the same as the slope here. So let the pattern take over. As long as x is 3, the slope is 4. All of the line segments that I've drawn here, I tried to draw in with a slope of 4. All of the line segments that I drew here, I tried to draw with a slope of 3. slope of 2 down this column, slope of 1, slope of 0, slope of -1, slope of -2. So some of these are going to be easier than others because whenever the derivative depends only on x or y, there are patterns that are more easily exploitable. We are going to talk about one more within this video that's a little bit more difficult to determine, but we'll go ahead and talk about that one next. So the reason why this one's going to be a little bit trickier to figure out is because if you look at the derivative depends on both x and y. When the derivative only depends on one variable, when the differential equation only depends on one variable, the patterns are a lot more obvious. There are still patterns here. You can kind of see right here all of these slopes ended up kind of forming a straight line, and we'll talk about why as we get into this. You'll see a pattern down this diagonal, but I took the same approach. I said I'm going to start up here. So when I start here at the ordered pair 3, 2, and I didn't do the table for this one. I was just kind of tracking everything in my head. If you're more comfortable building the table, as long as it's not like a timed scenario, then go for it. But if you're trying to do this as quickly and as efficiently as possible, you can keep track of this in your head. It's usually not that difficult to do. So at 3, 2, 3 plus 2 gives me a slope of 5. So there's a slope of 5. I'm going to do the same thing I did before. I'm going to move over 1 unit. So now, if this is a slope of 5, what type of slope am I going to have to show here? So that's 2, 2. Slope of 4, right? 2 plus 2. So the slope had to go down slightly here, still stay pretty steep and stay positive, but down slightly. So I moved to the left one unit, and my slope decreased by 1 unit, again within this slope field, as it did with the last one. I'm going to move to the left again. So at this spot, what's my slope going to be? So what's that? 1, 2, 1 plus 2 is 3. So yeah, if that's a slope of 5, 4, 3, 2, 1, 0, -1. Go to your next line. At this spot, I'm at 3, 1. 3 plus 1 is a slope of 4. So these slopes are no longer the same down this column. This slope and this slope have to be the same, right? I got 4 for this slope, and if I put in the ordered pair 3, 1, I get 4 for this slope. So I tried to draw these segments as close to being parallel as I possibly could. And then as I moved across this row again, I'm going to have the same pattern happen as I moved across this row. When I move to the left 1 unit, I'm going to have my slope decrease by 1 unit. So slope of 4, 3, 2, 1, 0, -1, -2. Go down to your next line. This is 3, 0. 3 plus 0 is 3. So the slopes down this diagonal all had to be positive 3, and I tried to draw those segments as closely to being parallel as I possibly could, and then I'm using that pattern as I work my way across the line again. So 3, 2, 1, 0, -1, -2, -3. I did that for the rest of these, and before too long completed the slope field. So if you're building a slope field from scratch, that's how you go about doing it. In the last video that we're going to be looking at within this little sequence, we will talk about how to take a sequence of slope fields and match them up with the derivatives that they came from.